Hi, welcome back. In the previous session, we have learned how to find the unit digit of a number raised to any power. In this session, we will learn the last two digits of a number raised to any power and also the last non-zero number or the first non-zero number from unit digit or the last non-zero number of a number. Now, power cycles is a very important concept. Though the weightage given to power cycles in numbers is very limited, this pie chart will give you an idea about the various numbers concepts asked in common division test in the last 25 years, in which the power cycles is like we have got only 6 questions and the weightage is 3%. However, in the last 3 years, that is CAT 2012, 13, 14, every time the power cycles question has appeared. Let's see. The four concepts that you need to learn in numbers is n raised to power p, some number, what is its unit digit, what are the last two digits, and the non-zero number. So in the previous session we have learned the unit digit one. In this session we're going to learn last two digits. And do remember, the power cycles is quite a simple topic. We have already covered all these things during our school days, and particularly this is the application part of binomial theorem. So it is not at all a shortcut or shortcut technique. Let's see how we can classify the numbers. The first thing is to find the last two digits of n raised to some power p, that is that we need to find the last two digits. Now, I'll classify these things into two types actually. One, a number ending with 1. That is given number ending with 1. With this one, I'll take forward to a number ending with 5. So we have the same methodology to find a number ending with 1 and a number ending with 5. And by using this one, we can find the number ending with 379, that is the remaining odd numbers. And for the even numbers 2, 4, 8, we have a method, and by using these two, we can solve a number ending with 6. So provisional there are two methods, that is number ending with 1 and numbers ending with 2 or 4 or 8. That's it. Let's first find out a number ending with 1. Now, if we take like 11, that's a number ending with 1, and raise it to some power, as we have done it in a cyclic order when we are trying to find the unit digit of the number. Here as well we will take a cyclic process. So 11 power 1 is 11, that's what we can ignore. 11 square is 121, 11 cube is 1331, 11 power 4 is 14641, or if I have to take, let's say, 21 square, that is 441, 21 cube, that is 9261, or if I have to take like 71 square, that's very easy, 5041, or if you ask me to find 71 cube, that's a number ending with 11, or if you ask me to find like 91, let's take any number, 91 square. 91 square is a number ending with 81. 91 cube is a number ending with 71. Well, our primary concern is to find the last two digits. Unit digit is anyways 1. That's very easy. A number ending with 1 raised to any power, its unit digit is going to be 1. Now the last two digits, that is the tens digit, that is the most important one. Now look at this one, tens digit we can get, that is like, this is 2, that is 1 into 2, that is 2, 1 into 3 is 3, 1 into 4 is 4, 2 into 2 is 4 here, 2 into 3 is 6 here, 7 into 2 is 14, that is by 4, 7 into 3 is 21, that is 1, 9 into 2 is 8, that is 81, 9 into 3 is 7, that is 71. What we have done is quite simple. We have multiplied the tens digit of the base with the unit digit of the power. If I have to give you in a simple format, that is this how it happens. If you have a number, let's say ABCD ending with 1 and it is raised to PQR, the unit digit is obviously 1, that is unit digit. Now this is the one important one, tens digit, that is the multiplication of d into r. What is d? D into r. D is the tens term of the base and r is the unit digit of the base. It's a very simple one. Very simple one. Now this is the application part of binomial theorem. I'm not showing you binomial theorem actually. This is what we need to learn. Binomial theorem and all we have covered in 10th class, and then we know how to solve the questions. But the application of the binomial theorem is extremely useful when we are trying to solve these kind of questions. Now we have done with one. Now the extension is going to be 5 here, a number ending with 5. First let's take some numbers. 15 square, that is 225. 15 cube, that is 3375. I'm taking 25. 25 square, that is 625. How much is 25 cube? That is 15625. Let's take some other number. 75 square, that is 5625. And 75 cube, that's going to be 75. 75 for 4, that's going to be 25. You take any number actually. Now if you observe closely, these numbers are either ending with 25 or 75. Look at this one. This is going to be 25, or else this is going to be 75. We have got only two different numbers. Either the last two digits as 25 or 75. Again, as we have done it for 1 actually, that's what we have taken d and r here. We can simply take the same thing here. We can simply consider it for a number ending with 5. So let me tell you, if we have a number, let's say ABCD ending with 5, and then I've raised it power to some PQR, let's say. Now unit digit is anyways 5. 5 raised to any number is going to end with 5. Now we need to consider the tens digit of the base and the unit digit of the power, which are d and r, that is d as well as r. Now if you observe these numbers, d can be even, r can be even. Well, d can be even, or can be odd. D can be odd, or can be even. And both d and r are odd. Now the simple thing is, whenever we have an even number, at least one even number, then the last two digits are 25. Otherwise it is 75. If both are odd, it is 75. If at least one of the numbers is even, then we have got 25. Quite simple. What we have done for 1 is like we have multiplied d with r, that is tens digit of the base and then unit digit of power. Here we have considered tens digit of base and then unit digit of the power. However, whenever both of them are odd, the last two digits of the expression are going to be 7 and 5, that is 75. Whenever any one of them is even, then it's going to be 25. Now let's extend this one. So we have completed it when it is for 1, and then we have extended it for 1, 5, and we have completed. Let's see the same thing. We will extend it for numbers ending with 3, 7, 8. These are odd numbers. Let's do a simple thing. Now let's see, we need to find 3 power 16. Finding the last two digits of 3 power 16 is what you need to know. Finding the unit of 3 power 16, that's very easy. We have done a cyclic process. We have raised the power from 1, 3 power 1, 3 power 2, 3 power 3, 3 power 4. So a power in a proper order starting from 1. That is an increasing order. Now let's try to see whether we can apply the same methodology. So that is 3 power 1, that's going to be 0, 3. 3 square ends with 0, 9. 3 cube ends with 27. 3 power 4 ends with 81. Now 3 power 5 ends with 243. 3 power 6 ends with 729. 3 power 7 ends with 2187. 3 power ends with 6561. Now if you observe all these numbers, that's last two is, that is 0, 3, 0, 9, 27, 81, 43, 29, 87, 61. Well, they're not matching. So when we have done it with cyclic process, actually, the cycle is not completed. It is continuing. How long can we continue? We need to save a lot of time. So how long can we continue? Since it is not providing us any clue here, we just need to draw some inferences. Now the first inference that you can draw is, I have given a clue that a number ending with 1 methodology is going to be applicable for a number ending with 379. What is the method? A number ending with 1, that is like AB ending with 1 whole power PQR. We know that it is 1 and it is B into R. So if a number ends with 1, then we can solve the question faster. And it's not going to take more than few seconds. Now, if a number ends with 1, that is the logic here. Now look at this one, 3 power 4 ends with 1 and as well as 3 power 8 also ends with 1. Both of them, 3 power 4. Now in such a case, 3 power 16 can be written as 3 power 4 whole power 4, that is 81 power 4, and unit digit is 1, tens digit is 8 into 4, 32, that is 2. That's very easy. Let's take 3 power 16 again. We use this one, that is like, this can be written as 3 power 8 whole power 2. So 3 power 8 is nothing but 6561 whole power 2. Since this is going to be unit digit is 1 and then tens digit is 6 into 2, 12, that is 21. Look at this, both cases, the last two digits are 21. Now in such a case, there is no point in going for 3 power 8 actually. 3 power 4 is the nearest one. 3 power 4 is what? The unit digit of 3 power 4 itself is 1. So that is the clue here. 3 power 4 unit digit is 1. If you identify that we have got 7 same methodology, if you know that 7 power 4 unit digit is also 1, whereas 9 square unit digit is also 1, then that's very easy. Whenever a number is ending with 1, we need to raise is up to power 4 so that the expression ends with 1 unit digit as 1, then that's very easy from that onwards. Now if you want to solve that 7 power 16, let's say 17 power 16, that is nothing but 7 power 4 whole power 16. Now knowing 7 power 4 unit last two digits are mandatory here. Anyway, I'm going to teach you one more concept, how to find the squares of any number, how to find the last two digits of any square quite easily. Now 7 power 4 last two digits, 7 power 4 is 2401, this whole power 16, that is nothing but 01 whole power 16, that is 01. That's very easy. Now let's say 9 power 16. 9 power 16 is nothing but we can write this as 9 square whole power 8. 9 square is 81. 81 whole power 16, that's nothing but 1. 8 into 6 is 48. It is 8. That's very easy. Now let's take a 2-digit number instead of a single digit number. We have a 2-digit number, let's say 13, and 13 is raised to 16. Now can we take this one as 3 power 16? Think, can we take only 3 power 16 or should we consider the last two digits? That is the most important one. So let's see whether we need to take last two digits or only single digit. Now if you want to find, let's say, last two digits of 13 square, which is very easy, we can say 13 into 13 exactly, that means it is 3 into 3 is 9. Now 3 into 1 is 3. Now 1 into 3 will come here 3, and then whatever comes, they come in the hundreds places. That's going to be 9 and this is going to be 69. Now to find the last two digits, we have used unit digits of both the numbers, that is 3 and 3, and also we have used tens digits of both the numbers 1 and 1. So we need last two digits. Let's see what happens if we have a 3-digit number. Let's take 123 whole square, that's going to be 123 into 123. Now 3 into 3 is 9, 3 into 2 is 6, and the remaining whatever come, they come in hundreds places and thousand places. Now next one is 2 into 3 is absolutely 6 here, whatever come, they come in the remaining digits, they come in the hundreds places. Now, should we multiply 1 into 3? If you are trying to multiply 1 into 3, what happens is like 1 into 3 will come here. That's going to be hundreds place, so that's not needed. So since we need only the last two, we don't need any other digits. Now observe which digits are involved. 1, the unit digit of both the numbers, that is 3 3, and hundreds digits, tens digits of both the numbers, that is 2 3. So it means the remaining digit, that is 100 digits 1 and 1, they're of no use. In such a case, what we can directly say here is, so if we have a number a b c d and let's say whole power p q r, and if you want to find the last two digits of the number actually, so then these are of no use, and our primary concern is only with this one, that is like cd whole power pqr. Remember, when we wanted to find abcd whole power pqr unit digit, actually we don't need the first three digits, we need only last digit, that is going to be d power pqr. So if you want to find the last two digits, we need the last two digits. If you want to find the last three digits, we need last three digits of the base. If you want to find the last n digits of a number, we need the last n digits of the number as well as all the digits of the power. Straightforward, simple. Yeah. Now here 13 power 16. Since we want to find the last two digits of the number, so we must consider the last two digits of the base, that is 1 3. Now 13 power 16. Now 13 power 4, we know that it ends with 1. That's very easy. 3 power 4 ends with 1. So obviously 13 power 4 also ends with 1. Now 13 power 4 is not a simple number. We cannot calculate here, even though calculator is available in this year's CAT actually. Now why should we use calculator? Before using the calculator, we can find it quite easily. Now 13 power 4 whole power 4. 13 power 4 is very difficult. That's why you can say 13 square whole power 8. Now 13 square is nothing but 169 whole power 8. Since we don't need this one, so we can stay away from this one, and then it's going to be down to 69 whole power 8. That's what we can write as 69 square whole power 4. Now 69 square is also a bit difficult here. If you don't remember 69 square, finding the square is very easy actually. Why should we really try to find 69 square? We need only the last two digits of 69 square. Let's see how to find the 69 square. I'll take the same number. Now we need to find 69 square last two digits. First let me explain you how to approach this one. Now if we have got, let's say 5, 6, 7, 8, 9, and I'm taking 10. On the other side of 5, we have got 1, 2, 3, 4. I take this as my root, and on the other side it's going to be positive numbers, and it's a decreasing order, so I say that it's minus. Now let's see 8 square. 8 square is nothing but 64. Now 8 is 3 places away from 5. That's the third digit from 5 on the positive side. Now take the third digit on the negative side of 5. That's going to be 2. Now 2 square is going to be 4. Now I'll tell you why we are doing all these things. Now if I say 5 to, let's say 9. Let's say 5 to 7. So 5 to 7 is nothing but 7 square, that is going to be 49, that is plus 2 sides. Now if I take minus 2 sides, that's going to be minus 2 number, that's going to be 3 square 9. Now check these two numbers. 2 square ends with 4, 8 square ends with 4, 7 square ends with 9, 3 square also ends with 9. Well, it's not about only taking root 5 actually. So you can take some other root, that is 10 actually. Now if I say that on the positive side of 10, that is going to be 11, 12, 13, 14 and so on. This is going to be the decreasing side, that's going to be, I can set it as negative. So from 10 to, let's say 12. That is 12 square is 144, unit term is 4. Now the deviation on the other side, that's going to be 8 square, that's going to end with 4. That's 4. What is this 5 and what is this 10s actually? These are very simple. 5 and 10 are multiples of 5. So if at all, if you have a number that is two numbers, whereas 5k plus x whole square and 5k minus x whole square. These two numbers end with the same unit digit. I'm going to apply this kind of simple concept to find the last two digits of the number. Let's see how to find the last two digits now. We'll take the same approach to find. Now, I have got 25. On the positive side of it, I've got 26, 27, 28, 29. The negative side of it is going to be 24, 21, 22, 23, 24. Now, let's see the 27 square, that is plus 2. So 27 square is nothing but 729. Last two digits are 29. Now take the same deviation on the other side, that's going to be minus 2. So 23 square is going to be 529. Look at this one, last two digits are same. Now let's take 29 actually. So it's plus 4. So 29 square is 841. Last two digits are 41. Now that takes the same deviation on the other side, that's going to be minus 4. So 21 square is 441. So the last two digits of the numbers which are equidistant, not of the numbers, the last two digits of the squares of the numbers which are equidistant from 25 are same. Can we apply for some other number? Is it only applicable for numbers where the deviation is taken about 25? No. You can have some other. Take from 50 also. Go other side. Let's see 53 square. And let's see 47 square. These are quite simple. So this deviation is plus 3. This deviation is minus 3. These are very easy. Very easy to find. How much is 53 square? Last two digits. Our primary concern is to find the last two digits. So that's going to be 2809. So that is 09. Now find 47 square. That's going to be 2209. Look at this. Last two digits are same. So in such a case, we can easily conclude that the deviation taken about 25k plus x whole square is same as 25k minus x whole square, and that's same for 50. You can say instead of k, you can directly say 25 plus x whole square, 25 minus x whole square, 50 plus x whole square, 50 minus x whole square, 75 plus x whole square, 75 minus x whole square. They take the same last two digits. Now let's go back to the question. The question we have asked is 13 power 16 last two digits. That's going to be 13 square whole power 8. 13 square is 169 whole power 8. Since we need to find the last two digits, we need to consider only 69 power 8. 69 power 8 can be written as 69 square whole power 4. Now we need to find the 69 square last two digits. Now 69, we can take a deviation about 50. So this is plus 619. Now if you know 69 square, that's very easy. That's very good. If you don't know, then take the minus deviation. That's going to be 31. Now 31 square and 69 square, the last two digits are same. If you know that 39 square, that's very good. If you don't know, then now you can take the deviation from 25. That is what you can apply. This is plus 6 deviation. Now this is minus 6 deviation. That's going to be 19. So 19 square, 31 square, 69 square, they all end with the same last two digits. In fact, you can extend on the other side also. So you can take a deviation from 75 and say this is minus 6. Now you can take plus 6. That's going to be 81. Now 81 square also. So 19 square, 31 square, 69 square, 81 square, and you can go on. All these numbers end with the same last two digits. Now here 19 square is 361. So if you know the squares of the numbers up to 25, that's very easy. Then you can find the answer quite easily. So 19 square is 361. So as well as 69 square also ends with same 61 or 4. That's now easy. A number ending with 1. So 6 power 16 to 4 is 24. That is 41. Very, very easy. This is the application of binomial theorem. I'm not telling you that these are the shortcut techniques or these are tricks actually. Well, this is the application part of a binomial theorem. We are not showing you the how we applied actually. Now to find 17 power 16, so you need to find 17 power 4 whole power 4. That's bit difficult. That's why stick to 17 square whole power 8. 17 square is 289. 289 whole power 8. Since we don't need 2 here, since we need only last two digits, so it's 89 power 8. So that is 89 power 8 can be written as 89 square whole power 4. Now 89 square, how to find 89 square? So 89 square we can take a deviation from 75. That's going to be plus 14. Now we can focus on minus 14. Minus 14 is 61. If you know 61 square, that's you can apply. If you don't know, then take a deviation from 50. That's going to be plus 11. Now take minus 11. That's going to be 39. If you know 39 square, that's okay. If you don't know, then take the deviation from 25. That's going to be plus 14. Now take minus 14. That's going to be 11. So 11 square, 39 square, 61 square, 89 square, they all end with the same last two digits. So 11 square we have got 21. You can do the other way. Should you take every single deviation from 75, 50, 25? No, you can take a deviation from 50 directly. So this deviation is plus 39. Now you can take the deviation. That's going to be minus 39. This is the application of binomial theorem. So we have done it for 1, and based on it we have done it for 5. Now we have already finished 3 numbers ending with 379. Now let's focus on the numbers 2, 4, 8. These are the even numbers. Numbers ending with 2, 4, 8. With this one we can focus on 6. Let's take 2 power 2, 4, 8. Now we will do the same process, that is 2 power 1 is 0, 2. 2 square is 0, 4. 2 cube is 0, 8. 2 power 4 is 16. 2 power 5 last two digits are 32. 2 power 6 last two digits are 64. 2 power 7 is 128. Last two digits are 218. 2 power 8 is 256. Last two digits are 56, 5 and 6. 2 power 9 it's 1, 2. 2 power 10 it is 1024. Now I just continued up to 2 power 10. Now, so we started at 2 power 1 and we reached 2 power 10. Still there is no matching here. It seems that cycle is not completed. To find the last unit digit, the cycle size is 4, but to find the last 4 digits we have done the same process, cyclic process, but it provided us no indicator. Now what can you do is like quite simple. So you cannot extend 2 power 11, 2 power 12, 2 power 13, but it seems that there is no end here, knowing where to stop and all. If you have no idea, then it's like wasting a lot of time. What we can do is like, we know that it's very easy to remember up to 2 power 10, that is 1024, which is 24. Now how can we apply this one is like, let's see 2 power 20, that's going to be 1024 whole square, that's going to be 24 whole square, that's going to be 576. Now it is 76. Now let's focus on 2 power 30. 2 power 30 is nothing but 2 power 10 whole cube, that's going to be 1024 whole cube, that's going to be 24 whole cube, that's going to be a number ending with 24. Now let's focus on 2 power 40. 2 power 40 is nothing but 2 power 10 whole power 4, that's going to be 1024 whole power 4, that's going to be 24 whole power 4, that's going to end with 76. Do you observe any pattern here? Yes, there is a pattern. 2 power 10 ends with 24, 2 power 20 ends with 76, 2 power 30 ends with 24, 2 power 40 ends with 76. So you can write this one in a simplest way. 2 power 10 whole power 1, 3, 5 and so on. The last two digits are 24. 2 power 10 whole power 2, 4, 6 and so on. The last two digits are 76. You can write it the other way. 2 power 10 whole power odd, it ends with 24. 2 power 10 whole power even, it ends with 76. Now how about finding 2 power 15, 2 power 13 then? So 2 power 15 is very easy, right? Now this can be written as 2 power 10 into 2 power 5. 2 power 10, that is like 2 power 10 whole power 1, that is odd, into 2 power 5. So what is odd? 24 into 2 power 5, that's 32. 24 into 32. You can find it for any number. Let's take it. Why should we say that 2 power 15? We can say 2 power 75 also. That's going to be 2 power 10 whole power 7 into 2 power 5. So 2 power 10 whole power 7 is odd. 2 power 10 whole power odd is 24. So 24 into 32. That's very easy. Now, one more thing that you can observe closely is, if we have 2 power 10 whole power even into 2 power x, where x is any number greater than or equal to 2, and we know that it is 76, and this is 2 power x. Last two digits of 2 power 10 whole power even is 76. Now if x equal to 2, that's going to be 76 into 04, because it's 2 square, that's going to be 04. 76 into 2 cube, that is 08, it ends with 08. 76 into 2 power 6, that's going to be 64. So 76 into 64 is 64. So you can easily say that 2 power 10 whole power even is multiplied by a number that is 2 power x, where x is greater than or equal to 2. We can say the last two digits are same as 2 power x last two digits. This is quite simple. Now to find the unit last digit of 6, that's very easy. Last two digits of 6. Now we can, let's say we want to find 6 power 16. That's very easy. We can write it as 2 into 3 whole power 16. Now we need to find 2 power 16 last two digits and 3 power 16 last two digits, and we need to multiply them. That's very easy now. Now what we have done is, if a number ends with 1, then that's very easy to find. With this one, we reached a number ending with 5, and we have used the same methodology. That is like we have used the tens digit of the base and the unit digit of the power. Now by using this one, we have interlinked with 3, 7, 9, which are odd numbers, whereas 3 power 4, 7 power 4, 9 square ends with 1, so that we can apply a number ending with 1. Now 2, 4, 8, these numbers are the form 2 power x actually. We can find it quite easily. That is like 2 power 10 whole power even ends with 76, 2 power 10 whole power odd ends with 24. If you are confused between 24 and 76, quite simple. Put 2 power 10 whole power odd. What is odd? 1. So 2 power 10 whole power 1, that is nothing but 2 power 10, that is nothing but 10 24, that is 24. So if at all, if you are confused between 24 and 76, just substitute 2 power 10 whole power with 1. Now with this one, we reached 6 also. That's it. Now in the same video, you can find 14 questions, exactly 14 questions. These are question number 1, 2, where you need to find the last two digits. These are question number 3, 4, question number 5, 6, 7 and 8, question number 9, 10, where you need to find the last two digits. 11, 12, again the last two digits. Now 13 and 14, you just need to find the first non-zero integer from the right of number, and 14 also. These are the 14 questions. You can solve them. In the next video, I'm going to give you the solutions for all these 14 questions. And non-zero integer, that is from the right of 3 power 123. That's very easy. Try on your own. If at all, if you feel that you are unable to get it quickly, then you can absolutely watch the video. Now solve all these 14 questions. With this one, I finish power cycles, power cyclicity of numbers. Then once you have gone through the video solutions for this worksheet, you can solve all the CAT questions. There are 6 CAT questions given on power cycles. Solve all of them. The worksheet for all the 6 questions is available in Facebook page of KISH CAT classes. And then also the next video is going to be the solutions for this worksheet, and the second one is for the original CAT questions. Thank you.